Welcome everyone. So it's my pleasure to introduce Professor Fred Adams. Most people probably have heard about Fred's name through reading the annual review article of 1987, Should Adams Lozano, which is the most famous paper or review for star formation that everybody has to start their career with. Okay, so now he's here live in person, and he finished his he got his undergrad degree from Ohio State.
No, Iowa State.
And then he's a PhD from UC Berkeley with Frank Shu in 1988. Then he went to Harvard Smithsonian for postdoc for 3 years, and then he went to University of Michigan and became a professor all throughout the years. And here he's standing in front of us. As we know from the introduction, as I sent, he's currently the Taiyu Wu Collegiate Professor of Physics and Director of the Line Weber Center for Theoretical Physics at University of Michigan. And he has numerous papers that ranges from cosmology, star formation, planet formation, theories of origins of everything. And he's also the author, one of the authors of 2 or 3 popular books. So that's here talk, and welcome him.
Well, thank you, Sienna, for the kind introduction. Thank you all for coming out, and thank you for hosting me for this couple weeks and giving the opportunity to talk. So as Sienna said, we spent a lot of our time in the early parts of our careers putting together a theory of star formation, which is codified in the 4 stages paradigm that we talked about. What I'm going to talk about today is an attempt to do the same thing for the theory of planet formation. And you'll see how far we get, how well we're doing, how well we're not doing, and what the current state of the art is. So let me give you a brief outline of what I'm going to talk about today. Since we only have an hour, we can't talk about everything. I'm going to give you a whirlwind tour of the observational landscape of what exoplanets look like. I'm going to give you a very brief overview of 2 different paradigms for forming planets, one from the top down, one from the bottom up. I'm going to focus on the latter because that will form most of the planets. That's one of your lessons for today. And I will talk about the stages of the core accretion paradigm. And then within that, what I want to do is I want to develop a completely analytic treatment, well, as much as I can, of exactly how all the physical processes happen for the planet formation process. And then at the end of that, we want to look at where we are in terms of identifying these things in the sky. Can you actually look at the spectral energy distribution of a forming planet and identify it as such? And then at the end, for the second half of the talk, I want to construct a working theory for how you actually calculate the distribution of masses of forming planets. Now, about a dozen of you I recognize from the Friday summer student talk. For those guys, you guys, thank you for coming back and suffering through yet another talk by me. The first half of this you will find quite familiar because it's going to be a whirlwind tour of Friday's lecture. It's a whole weekend ago, so you might not remember everything, but there will be some overlap. Okay, so let's jump into this. So let me begin by naming my main collaborators from the papers I'm going to deal with today: Michael Meyer, Arthur Adams, who's got the same name but otherwise no relation to me, Konstantin Batygin at Caltech, and my new grad student, Astor Taylor. So every talk with planets begins with this picture where you show the masses of the planets we've discovered to date as a function of their semi-major axis. The planets we know from the solar system are listed here. They're right at the bottom level of this. It's easier to see planets close, and it's easier to see planets that are big. So planets that are far away and small are hard to see, and we can sort of barely see them. But we've discovered up to 5,000 planets to date. So we're starting to have a bit of a sample where we can actually say what the distribution of planets look like, and I'll say a few words about that. The other thing that we want to emphasize is that stars or planets form in circumstellar disks, and circumstellar disks form around stars. We can now, for the first time in history, as of, well, a few years ago now, take pictures of these disks. So we actually have a pretty good idea of what the disk properties are, and these disk properties set the initial conditions for the planet formation problem. Nicely, it turned out that most of the disk properties that we can now measure and say with some certainty are actually those that we predicted back in the 80s and the 90s. They're kind of commensurate with that. To give you an example of that, the size of this particular disk is 100 AU. If you look at the prediction I made in my thesis, it's 100 AU. This is also 1988. So this was long before ALMA was even an idea. Now, we of course don't just measure one disk, we measure bazillions of them, and to 0th order, disks are 100 AU in size, okay? They're not all exactly the same size, but to 0th order of magnitude, disks are 100 AU in size. In fact, we can put all the observations together, and if we put all the observations together, this would be a 40-hour talk. And to distill 40 hours of talk down to one slide, these are the disk properties that we can say. The star formation process naturally produces disks. Why? Conservation of angular momentum. Because the initial states for forming stars are rotating with non-zero angular momentum, the material that falls cannot fall to the stellar surface. It must fall to a larger radius. That larger radius is a disk. The larger size of that larger radius is 100 AU. So disks naturally have radial sizes of 10 to 100 AU. You'll recall our solar system lives at 30 AU. That's the outer boundary of Neptune, exactly in this range. We're completely typical in that particular regard. The disks, we think, have a starting maximum mass of about 1/10 that of the star. If you pile more mass onto the disk than that threshold, it will become gravitationally unstable. It will adjust itself to stability, and then it will have less than this threshold mass. So while you're forming, you never get much bigger than this threshold of the 10% disk mass to star mass ratio, because you always adjust, or the system will always adjust to stability. And it has a mechanism to do it, namely gravitational waves. These gravitational stabilities are akin to the gravitational stabilities that produce spiral arms in galaxies, which was my advisor's thesis. That's what Frank Hsu and C.C. Lin did back in the 60s, right? But that physics is still true, and it still transfers angular momentum, and it makes you have this maximum disk mass. The surface densities of these disks can be described as power laws. The indices are between 1 and 2. We talked about that at some length on Friday. And the disks have a lifetime that's exponentially distributed, as I'll show you, and it has a characteristic time constant of about 3 million years. So the game is that we're starting with these 100 AU disks. Most of the working stuff that we care about are the rocks, and you'll see why. And they have sizes from a micron up to a centimeter. And then they somehow produce Jovian planets. So we go from 100 AU scale to a 0.00000 AU scale, all the way up to a 0.00001 AU scale. And we want to understand the physics of how we get from one place to the other. The other thing that we have finally put together is we finally got the giant planet occurrence rates. Again, I showed you this on Friday. If you plot the number of planets we see as a function of distance from the star, either in period or semi-major axis, you see it grows and apparently peaks. This is after you've corrected for selection effects. And the peak is at 3 AU on this plot. If I show you two more, they're at 3 to 5 AU. This, of course, is nicely coincident with the ice line. If you have a circumstellar disk, the inside's hot, the outside is cold. The outside is cold enough that ices can exist on the rocks. We call the line beyond which there's ice the ice line. One of those things in astronomy that's aptly named. Most aren't, but that one is. And it turns out that it's a lot easier to form planets outside the ice line because the rocks that are forming the planets have 3 times more mass on them, and ice sticks together better than sand. So those are true, very simple principles that really drive the process. So the sweet spot for forming planets is just outside the ice line. The occurrence rates I just showed you show that planets tend to form just outside the ice line. So that actually makes sense. Now, for those of you who are young, there was a problem because everyone said before 1995 that planets would form at the ice line preferentially, which we now see. But then the first planets we found were 51 Peg, which is a Jupiter in a 4-day orbit, which is way inside the ice line. So for 2 decades, people said, well, we were completely wrong because planets don't form at the ice line. And then after we got enough data, it's like, oh, they do form at the ice line after all. So never mind those 2 decades. Planets form at the ice line, which leads to the question, how do you make planets at the ice line, okay? Well, there's 2 ways to make planets, as I said. You can make them from the top down, and you can make them from the bottom up. Let me briefly talk about the top down scenario, and then I will dismiss it. Spoiler alert, okay? The first actual simulation of forming planets by giant instability I actually did by accident as a postdoc. We were trying to make stars in circumstellar disks, and we couldn't. No matter how massive you made the disk, you never actually formed a secondary body that was anywhere near as big as the star. You always got a 10, 20, 30 Jupiter mass thing. Now it's a very important mass scale, 10, 20 Jupiters. That's not a star. It's also not a planet. It's a brown dwarf. And you always form the secondary in the outer part of the disk. The disks are 100 AU, so the natural formation mechanism of gravitational stability produces brown dwarfs at 100 AU. Now, this was published in 92, so this work was done in 1990. Those of you who remember 1990, our computers were not that good. So if you dial yourself forward in time 20 years, Zhao Anju did a whole much better job of this. He's a Michigan graduate who's now a professor at UNLV in Las Vegas. And he did a wonderful numerical job, and he found that when you have gravitational instability in disks, 1, you need a heavy disk, as we knew. 2, you get brown dwarfs at 100 AU. Now, many, many simulations, including a recent one by Jim Stone at Princeton and his friends, found that you get brown dwarfs at 100 AU. And when we look at image planets, sometimes we see brown dwarfs at 100 AU. So what I'm going to conclude here is that gravitational instability as a mechanism for 4 planets is actually a good way to occasionally form, wait for it, brown dwarfs at 100 AU. Now, brown dwarfs at 100 AU are not Jupiters at 5 AU. Remember the occurrence rate plots I showed you about 5 minutes ago. They peak with Jovian planets at 5 AU. The gravitational instability mechanism produces brown dwarfs at 100 AU. So it's a great mechanism for producing planets in this upper part of our diagram we started with. But it doesn't account for all of these. So we need another way to make all of these. And to focus on what we're going to talk about today, I'm going to ignore the rocky parts. In some sense, the lower mass planets are just failed instances of the larger planets, but the actual physics I'm going to talk about applies mostly to these larger mass planets. And we think they formed through the core accretion paradigm. So the core accretion paradigm can be codified into 3 different stages. The first stage, aptly called phase 1, is to build a great big rock, okay? So the first step is that rocks accumulate into bigger rocks and into bigger rocks. This process happens or continues until the rock is about 10 times the mass of Earth. Now that's an important threshold because once the rock is 10 times the mass of Earth, it's got strong enough gravity to start to hold on to gas. So it can accrete gas. If it has less than about 10 times the mass of Earth, its gravity is too weak and gas doesn't like to stick. So then once the rock gets that big, we enter into phase 2, where both rocks and gas can accumulate onto the forming planet. But here's the thing, as long as the gas is tenuous, as long as the gas envelope has less mass than the core that it's sitting on, it doesn't have much self-gravity and it will be physically large. If it's physically large, it will be so large that it fills what's called its Hill sphere, which means it's so big that the outer parts of it don't actually belong to the potential well of the planet that's forming, but rather belong to the potential well of the star in the background, which means that it can't join onto the forming planet. So in order for more mass to join onto the forming planet, that tenuous envelope has to cool down, and cooling down takes a long time. So this phase 2, where we have to cool down to grow bigger, takes a while. But once the mass of the envelope is big enough, its own self-gravity crushes it. It makes it geometrically small. Once it's geometrically small, then material entering the Hill sphere can accumulate rapidly onto the forming planet. And we enter into phase 3, the runaway gas accretion phase. So just to show you this in a couple different ways, we have stage 1, which is the accumulation of rocks. We have stage 2 with an outer boundary at the Hill radius. The Hill radius is typically about 1/100th of an AU, or maybe as much as 5% of an AU if you're forming a Jupiter at 5 AU. And then later on, this atmosphere gets crushed and we form a planet. And significantly, the planet has its own disk. In fact, I stole this icon from the star formation paradigm picture just to emphasize the analogy of it. So what we get during stage 3 is we have an outer boundary set by the Hill radius, mass inflow into the Hill radius. It's rotating and falling. It reaches ballistic trajectories just like in the star formation problem, and it makes a planet and a circumplanetary disk around it. In terms of timescales, these timescales vary, but it takes a good fraction of a million years to make the big rock, usually a couple million years for the atmosphere to cool, and then who knows how long to accrete the rest of the mass. It depends on how fast it comes in and how big the planet is in the end. But all of these timescales are significantly of order of magnitude a million years. And that's important because remember, the disk lifetime is only 3 million years-ish. So if the planet formation problem were a whole lot longer than 3 million years, you'd never make a planet because the disk would be gone before you could make a planet. And if you made the planets on a timescale much less than 3 million years, then the disk properties wouldn't matter. You would just make them instantaneously. So the fact that they're commensurate timescales is in fact important. So what I want to do now is I want to go into a little bit of detail to understand the physics of what this last stage of planet formation looks like, okay? So to remind you, during this last stage, most of the mass of the planet is accumulated. So this last stage is important for determining the mass. Now, one of the things that is not completely new, but more or less new, is that up until kind of sort of recently in history, when people have been looking at the planet formation problem, they've sort of ignored the rotational aspect of it, and they've done the spherical problem. Now, that makes perfect sense. You always do the spherical problem first. But it turns out that just like in the star formation problem, there's so much angular momentum in the system that most of the material that comes into the Hill sphere that eventually lands on the planet can't actually land on the planet. It has to land on a circumplanetary disk first. And then the disk physics determines whether or not and how and when the material that lands on the disk makes it to the star, or the planet. So disk physics is important, and it's not fully studied, okay? Now, in order to understand the disks, the first step is to understand how material gets from the Hill radius, or the Hill sphere, which is bounded by the Hill radius, down to the midplane where the disk is. And since the disk physics and the disk structure and the disk evolution will depend on where that material starts, we need an infall solution that tells you how material gets from the Hill sphere to the midplane, okay? This, of course, for those of you who do star formation, this is the analogy of the infall collapse solution for star formation that we've been studying for decades. But we need the analog of that for planet formation. Once we have that, we get the solutions for the density and velocity fields of that infall. That will tell us what sources the disk, and then we can solve for the disk structure. Also, just like in the star formation problem, the inner disk of the planet problem will be truncated by the magnetic fields on the central object, and that will set the inner boundary condition. And then just like in the star formation problem, there's several sources of luminosity. And then once you have all of these pieces, you can calculate the spectral energy distributions and see what forming planets look like. And since this isn't a mystery story, I'll give away the whodunit. We're now on the cusp, just now, this point in history, we're now on the cusp of finally being able to look at planets in the process of forming, calculate their spectral energy distributions, and determine their properties. We've got like 3 objects and a dozen data points. As in, this is very much just the beginning. But in a decade or now, there'll be a whole flood of data coming. So we're right at that point in history where we're first able to calculate these spectral energy distributions and compare them to data. And you have that to look forward to in about 20 minutes. Okay. So let's look at the physics of this in a little bit more detail. So the picture you should have in mind is that we have a forming planet. It's going to be kind of sort of near the ice line on average, but it could be anywhere. And there's a star here. There's a radius around the planet, which is the outer boundary of its sphere of influence. Turns out there's not just one radius of boundary, there's 4, because ain't nothing easy. And I'll tell you about that in the next slide. You can think of it as a Hill radius, and usually it is a Hill radius, but there's actually 4 of them, not 1. So there's boundary. Material from the circumstellar disk is fed into the vicinity of the planet, into the sphere of influence of the planet. So one of the variables we have to specify is the mass infall rate into the Hill sphere. Importantly, not every proton that enters the Hill sphere stays in the Hill sphere. Some fraction go back out. So just to be clear, when I talk about the infall rate into the Hill sphere, I'm talking about the net infall rate into the Hill sphere. So it's the stuff that goes in and stays, or the total that goes in minus the stuff that goes back out. So it's the net infall rate. Because there will be fluid flow where some trajectories just come in and go out. But we care about those that stay. So at any given time, you have to specify how big the mass is of the star or the planet that's forming. You have to specify the net m dot mass infall rate that I described. You have to say where the planet is, as in what its semi-major axis is. And then you have to say something about its inner boundary condition as determined by the surface field on the planet. So what we would like ideally is we would like a completely analytic description of the whole structure of this forming planet with an infall region, a disk, and a central object as a function of these 4 variables. Yes, Koichi.
I do not understand the definition of A.
A is the semi-major axis.
Okay.
So it tells you how far from the star you are.
What is C and eta?
C and eta I did not describe. So C and eta are basically efficiency factors that determine how much of the total amount of mass ends up staying. So you don't have to worry about them. They're all wrapped up into this net m dot.
Thank you.
Yeah, good question. I probably should erase them from my slide. Yes, Tom?
You need to worry about the mass of the star. Doesn't that come into the Hill radius?
Yes.
Is that, so your mass is here sort of in units of that?
Right, yeah. It turns out that almost all the planets that we see are, especially most of the Jovian planets, are around stars from about 1/2 to 1.
Okay.
Yeah, and we see nothing around 10 solar mass stars, and there's a huge deficit of Jovian planets around M stars. So for that reason, you're absolutely right, but I don't care because the mass range is so small. Okay, but it's a very good point, and I'm going to gloss over that for the rest of the talk. Okay, but you're right to call me out on that. So, like I said, there's actually 4 boundaries. There's the Hill radius. The Hill radius is the moral equivalent of the Roche lobe, which just tells you where the potential of the planet wins against the potential of the background star. And as you correctly pointed out, it has the mass of the planet and the mass of the star in it. There's also the Bondi radius. So for a given sound speed, the Bondi radius tells you whether or not the sound speed is big enough to fight the potential well of the planet. For most of the cases we care about, the Hill radius is smaller than the Bondi radius, so the Hill radius is the important factor. There's also the disk scale height, where I mean the disk scale height of the circumstellar disk. Most of the time, the disk scale height is bigger than the Hill radius, so the Hill radius is embedded in the disk. If you get to late stages where the planet becomes very large and this scale height becomes very small, then the disk or the Hill radius pops up through the disk, and you have to start worrying about finite circumstellar disk effects. And then just for completion, not everybody remembers this, but there's also an astrodynamic sphere of influence, which is slightly different than the Hill radius, which tells you if you have a satellite flying through the planetary system, there's a place where it starts to be influenced by the planet more than its background star, which is not actually the same, but it's almost the same as the Hill radius. So there's actually 4 boundaries you've got to keep in mind, although we're primarily going to talk about the Hill radius, and I will just talk about the Hill radius. And you have a question?
Is the disk cold enough?
Is the disk cold enough? Yes. I mean, the disk is cold enough that, I mean, at any given location, there's a sound speed, and that goes into, this is the sound speed and this is the sound speed, which depends on the temperature. And the disk is cold enough that mass can accrete. One of the things that you'll find, which is beyond the scope of what I wanted to talk about today, but I can see where you're going with this, so I'll explain it to you. When you're shoving all this material into the Hill radius and putting it onto the disk in the middle and the planet in the middle of that, this only works if the material coming in, can cool sufficiently. If you heat it up, you have a very, very dynamic equation of state with this very stiff, then you can actually make the infall rate so high that the planet gets so hot that nothing more can come in. If you reach that state, you won't form a planet. So I'm not going to talk about that state because that doesn't work. You'd never form a planet. That would be a theory of not planet formation. So in order for planets to actually form, you must have cooling. Otherwise, nothing that I say works. So I'm going to assume that we have cooling. Now, it's plausible that we have cooling, but nonetheless, if you don't have cooling, then none of the accretion picture that I described will be operative.
In first order approximation, I understand.
Yeah.
Thank you.
Okay, so let's just jump into some specifics. So if I start with trajectories at the Hill radius and I solve the equations of motion, I can calculate the velocity fields and I can calculate the density field. And those of you who do star formation will recognize the analogs of these formulae from the star formation problem. Since this is a colloquium and not a math seminar, we can simplify them. And what you find when you simplify them is that for a spherical input, the density distribution looks like r to the minus 3/2 on the outside and more like r to the minus 1/2 on the inside, where the boundary between the two is the centrifugal barrier. What's interesting in this problem is that the natural place for the centrifugal barrier falls at a third of the Hill radius. In the star formation problem, it's not so simple, but here it's a third of the Hill radius. These are the trajectories of the rotating infall. Since I'm showing a profile of them, they look like straight lines, but they're really like coming out like this as they go down. They're like rotating as you go in. Now the material falls onto this midplane, and this forms a circumplanetary disk. So once you have the source terms, which we do here, you can calculate where everything falls, and then you can solve the equations for the surface density of the disk, and miraculously you'll get simple analytic forms. Now they're not that simple because you get weird arc hyperbolic tangents and stuff, but you can do it completely analytically. Interestingly, if you go back to this picture, the formulae I just showed you are for an isotropic flow into there. You can also introduce an angular dependent flow that's either more concentrated along the poles or more concentrated along the equator. And you can do the whole analytic treatment for that as well. I will not torture you with those formulae, but I have them in my pocket if you want them. And then we can even simplify them further, because to 0th order, as you can see from the actual plot of those, the surface density profiles for the circumplanetary disk look a whole lot like just a 1/r profile. The magnitude of the coefficient in front depends on the size of the viscosity. As you make the viscosity larger, the steady state solution reduces to a lower value of the surface density. And in the limit that the viscosity goes to 0, material just stays where it falls. And you get the upper curve, which is also almost 1/r. So we have the surface density profiles in hand, and we can do that as a function of both infall geometry and as a function of viscosity. Now let's look at the inner boundary condition. The inner boundary condition is set by the magnetic field. There's two important magnetic field radii defined here. The first one is well known. It's the magnetic truncation radius. If you have accretion through the disk and onto the planet, the magnetic field lines will truncate the disk at a well-defined magnetic truncation radius given by this crazy formula here where you take all these things to the 1/7 power. And the people in star formation are very familiar with this. That sets a maximum temperature for the inner disk, and that has a signature in the spectral energy distribution, although not a very strong one, but you can in principle see it. There's another radius that is kind of interesting. Because the infall is gentle, there's a last field line that can support through pressure forces against the ram pressure of the infall. So there's a last field line where material comes in here and doesn't push it down further. And then if material hits at this point, material falling to the left of it will fall onto the planet, and material falling to the right here will fall back onto the disk. So this is a funneling radius, which gives you an effectively wider angle of direct infall onto the planet, which you can calculate, and it has this value to the 1/9 power. Long story short, it actually makes your hovering radius of the planet a little bit larger than it would be otherwise. The other thing is that you can actually find it. So where we are is that for a given value of the 4 variables I mentioned, planet mass, semi-major axis, net infall rate, and magnetic field strength, I can calculate all the system parameters, the density profile of the infall, the velocity fields, the disk structure, and as I'll show you, the luminosity contributions. We can also generalize this. We can generalize this far beyond what we've done for the star formation problem, for you star formation people, because we can use different amounts of angular momentum. We can use different choices of the energy at the Hill radius. The natural thing to do is to assume 0 energy orbits, which is what you would get if you have a lot of parameter space or orders of magnitude between the outer boundary condition and your inner boundary condition. But since here we're at the Hill radius, we're not that far out, you might consider other values of energy. As I've already talked about, you can introduce angular distribution to the infalls, and you can also introduce different conditions for the outer boundary condition of the disk. And these are set by 3-body effects, which I can talk about later if you want. Point being that we can generalize everything I just showed you in 4 different directions. That's like 4 different papers that I'm not going to actually go through the solutions to. Only that, again, we have these things in hand. What I want to do instead is I want to talk about what these things look like. So in order to see what these things look like, we have to do a radiative transfer problem. So the radiative transfer problem is set up this way. You have a planet in the middle of the flow. You have a disk around it. The disk is truncated, as we just described. So that sets the maximum temperature of the disk. And then this whole planet and disk is embedded in the infall region that I described with a well-known density distribution. This, of course, is completely analogous to the problem of what a forming star looks like when it's forming, only this is a forming planet, okay? Now, the first order of business is to set the luminosity contributions. And we have formulae for all of them, and they're a bit of a mess. So let's just do this in words. Material falls from the infall region onto the disk and shocks and produces luminosity. That's one contribution. Material that lands on the disk does not know in advance that it's supposed to be part of a Keplerian flow. So it has to adjust its energy while conserving angular momentum and mix in. That gives a mixing luminosity. So you have a shock luminosity and a mixing luminosity on the disk. In addition, you have a shock luminosity and a mixing luminosity onto the planet itself. You have intrinsic contraction luminosity, at least in principle, from the planet, although while it's forming and its surface is being beat up by the infall, it doesn't have a chance to contract much. So its contraction luminosity is not always very large, but you can include it. And finally, because most of the material falls onto the disk, even after it shocks and mixes, most of it still resides in the disk and has to work its way onto the star through viscous evolution. So the viscous dissipation of the disk is another important luminosity contribution. Now, what I'm showing you here are the spectral energy distributions of just the planet and the disk, where I'm using the simplest possible cases where I'm considering a completely flat, geometrically flat disk. The different contributions show you how the different inner boundary conditions due to different choices of the magnetic field change, because you get different amounts of near-infrared radiation as you change the inner temperature of the disk. Now I want to add the envelope. Now to start with, you see my spherical cow. I'm going to take the non-spherical density distribution that we calculated in so much detail, and then I'm going to spherically average it. Okay? Now, it turns out that that actually doesn't erase most of the physics, even though you might worry that it would, because the main effect of rotation, rotation does two things. One, it gives you an angular dependence, which I'll show you in a second. But two, it keeps material from falling all the way in. So if you take the non-spherical density distribution and then spherically average it, you retain the deficit of material in the inside. That retains the right total optical depth of the envelope. And if you're doing a radiative transfer problem through an envelope, it's the total optical depth of the envelope that's the single most important variable for determining what that thing looks like, in terms of how red or blue it is, right? So you're actually getting most of your physics by doing the spherical average. And then you have a two-dimensional radiative transfer problem to do instead of a four-dimensional radiative transfer problem to do. Now the reason why I like that is because the two-dimensional one I can do analytically. I have complete analytic forms for it. For the two-dimensional case, and this is a highly flattened one that my student Aster worked through, you see you'll get rather flattened density distributions. Now you might ask, well, does this matter? Well, it depends where you are in parameter space. What I'm showing you here are three different codes and the spectral energy distributions from three different results. So the dashed lines just give you the different contributions. So just focus on the three solid curves. If you do the equivalent spherical envelope treatment that I described, you get the green curve. If you use a ray tracing code, you get the red curve. And if you use a Monte Carlo code, you get the purple curve. Now, they're all kind of the same as far as we care. There's a little bit of difference with the Monte Carlo code at long wavelengths, but that's mostly due to the fact that the Monte Carlo code can't do exactly the same problem rather than a difference in the radiative transfer. Point being that, to start with, and I'll generalize this in a minute, to start with, the simple analytic code is good enough. So let me show you what happens as we look through parameter space for the spectral energy distributions of forming planets. Remember, we have four variables. We have to specify the instantaneous mass of the planet, the net mass infall rate into the Hill radius, the location of the planet in AU, and the boundary condition as set by the magnetic field on the planet. So if I fix everything but the mass, I get a series of spectral energy distributions. As I make the mass larger, the luminosity goes up, as you expect, but the spectral energy distribution gets bluer. If I instead fix the mass and change the mass infall rate, As I make the mass infall rate, I make the optical depth of the envelope thicker, which makes the object redder. So you see, as I make m dot larger, the luminosity goes up, so the spectral energy distributions get brighter, but they also get redder. So more mass moves you blue, more infall rate makes you redder. Magnetic field strength monkeys around with the inner boundary condition and gives you more or less mid-infrared radiation. And finally, what happens as I move the planet inward and outward? Well, as I move the planet from a large semi-major axis down to a small semi-major axis, I'm shrinking the Hill sphere and I'm shrinking the disk, and I'm narrowing the amount of temperature range that both the envelope and the disk can sample. That has the effect of making the spectral energy distributions narrower. So as I make the location of the planet move in, the spectral energy distribution goes from wide to narrow, and it gets close but not quite to a black body. Okay? So these are the sort of spherical cow answers to what the spectral energy distributions look like. When I first began this a couple years ago, this was the data point we had. There's maybe a forming planet with maybe a couple data points. So over the last couple years, I had my student Aster do a full two-dimensional radiative transfer treatment on this problem. And they did a number of things. The key issues that go beyond what I've told you about already is that when you do this problem carefully with a self-consistent disk, the disk isn't flat. It has a geometrical height with a height to radius ratio of about 0.2. So it's not super puffy, but it's not super flat either. H over R is about 0.2. That gives you relatively more disk emission and relatively less envelope emission. Since they kind of compensate when you look at the full spectral energy distribution, it doesn't look that different, but physically that can play an important role in determining the parameters. Now, in doing that, one has to do a full 2D treatment and a self-consistent picture of the disk, which means to run one model, it takes weeks on a computer, which is a long time. Now, what people like to do these days is they like to run MCMC, Monte Carlo sampling, where you calculate bazillions of models and you sample through all the different parameters to see what works. Now, in order to do that, you can't take 2 weeks to run each model, otherwise it would take a Hubble time to finish your problem. So what we then did is we built a semi-analytic treatment that mimics the full 2D treatment, which basically gives you the fatter disk that we need. Otherwise, it's a lot like what I just showed you. And then we can look at the two sources that we have and run the MCMC on those and see what we get. So this is the state-of-the-art spectral energy distributions for forming planets. If we look at, there's 3 of them we've seen. I'm showing you 2. I'll show you the 3rd one at the end of the talk. But this is all the data we have as of like last week. And these are the 2 spectral energy distributions for 2 planets in the system. And you see we have a lot of data. The data don't all agree with each other. You can run an MCMC and run best fit models, and by doing that you get best fit parameters, including, and especially this is important, the error bars on them. And you see that for these particular planets, they're kind of large for 28 Jupiters, right? Their M dots are kind of small. What that means is that the planets that we can actually see are near the end of their planet forming lifetime. They've already got most of their mass, and their mass accretion rate is already decreasing. That kind of makes sense because that's the place where it's most easily to see planets. If planets are smaller in mass and they have a larger M dot, then they're more embedded and they fade into the disk more, and it's going to be much harder to see them. So it makes a lot of sense that these are the ones that we see first. But these error bars are kind of large, but nonetheless, you see a lot of different models will work because we have a deficit of data at long wavelengths. So one of the lessons of this is that, and I don't think any astronomer has ever said this before, we need more data. We need more telescope time. We need to fill in the rest of this to see what that is. And of course, we need more sources. These are just the first two. And again, I'll show you the third one later. But this is how well we can do. We're right at the point in history where we can finally, for the first time, identify planets that are forming, and we can calculate their spectral energy distributions. And to the extent that these error bars are correct, we can determine their parameters. We would like for these error bars to be much smaller, but we need much better data in order to do that. Now, I have about 15 minutes left, so let me wrap up the first half of the talk, and then we'll go into the second half. So far what we have is we've got a new description, or a more complete description, including an analytic description, of the last stage of the planet formation problem. We can analytically calculate the density velocity fields, the disk structure, the magnetic truncation of the inner disk. We can calculate the luminosity contributions and the spectral energy distributions. In the spherical limit and the equivalent spherical limit, we can do all of this analytically. We can also do the full 2D numerical radiative transfer problem, including thick disks, including a way to do MCMC, and including a way to determine the parameters of the forming planets. And this is all kind of working. But again, we need a lot more data to go further. Now, one of the interesting things that we see, again, this is for those of you who work on the star formation problem, is that there's one important difference between the way a planet forms and the way a star forms. What's the same is that there's a lot of angular momentum. So most of the material that comes from the interstellar medium in the case of star formation falls onto the circumstellar disk and then has to get onto the star somehow. In the planet formation problem, most of the material falls from the Hill radius onto the circumplanetary disk and then somehow has to get onto the planet. So in both cases, angular momentum is carrying the day. But here's the thing. In the star formation problem, the ratio of radii between the outer disk and the star is a factor of 10,000. 100 AU to 10 to the 11 centimeters. Factor of 10,000. The star formation time is 1/10 of a million years. So in the star formation problem, you have to squeeze the disk or contract it or move it by a factor of 10 to the 4, all in 1/10 of a million years. Now, in the planet forming problem, the ratio of the disk to the planet is only about 180, maybe even as small as 100. And the time you have is 3 to 10 billion years. So at most, I mean, if you turn all the knobs to one side, I have 100 times longer in time and 100 times less far to go, which means it's 10,000 times easier for the disk around the planet to work than the disk around the star. Now that factor of 10,000 is a little bit of hyperbola, but you get the point. It's a whole lot easier for the circumplanetary disk to do its disk thing and dump material onto the planet than it is for the circumstellar disk to somehow do disk accretion and dump material onto the star. And what that means is that because we think we understand a little bit about viscosity, a viscous disk solution works perfectly well for the planet formation problem and is completely inadequate for the star formation problem. So when you make a star, the disk gets massive so fast that viscosity just cannot keep up, and you have to invoke gravitational instabilities to move things, and that's probably the physics that works. In the planet formation problem, things happen much more quiescently, the dynamic range is much more favorable, and viscosity can keep up. So that's the key difference, I think, between the planet formation problem and the star formation problem. But as you can see from this discussion, there's a lot of overlap. Now, this picture is incomplete. There's a lot of things that people will object to that I have not included in this description, because planets move as they form, planets don't form by themselves so they can compete with each other for mass, and so on. The key thing, though, that I haven't told you about is, where does this all end? As in, I've specified an m dot, And I can even define an evolutionary sequence by, after the fact, specifying m and m dot versus time, or even location versus time. But I haven't calculated those things. So I can tell you what the structure of this forming planet is as a function of those input parameters, and I can build you a time sequence for any time sequence you want, but I haven't calculated that time sequence. That's the difference. So the key thing is, what stops this process? Why does the planet end up with the mass that it has? So what I want to do for the rest of the talk is I want to build a theory for the distribution of planetary masses. And if you're doing anything in astronomy, the mass distribution of your fundamental objects is in fact the most fundamental thing. If you're a galaxy person, you want to know the distribution of galaxy masses. If you're a star person, you want to know the IMF, the distribution of stellar masses. If you're a particle theorist, you want to know why the quarks have the masses they have, right? So here we want to know why giant planets have the mass distribution they do. So I'm going to assume that they form through the core accretion paradigm, and I want to see why they stop, okay? So here's the logic. We actually have a natural stopping point because the disks have a finite lifetime. But that doesn't work. As I'll argue in the next minute, the distribution of stellar life or disk lifetimes is an exponential, but the distribution of planetary masses is not an exponential. So the story cannot be just simply that the disk runs out of mass. If that were the whole story, then the planetary mass function would be an exponential, and it's not. So that's the wrong answer, okay? Let me say a little bit more about that. So here are the disk lifetimes. What I'm actually plotting is the disk frequency is a function of stellar, or age of star forming region. And you see that as time goes on, the fraction of systems with disks goes down. I can plot that versus exponentials, either in a log-log or a semi-log plot, or a linear or a semi-log plot. And I see that it's close to exponential. It's not a perfect exponential, but I can think of it as an exponential. And the exponential time constant is like 3 or 4 million years. So that means you can kind of consider the disk as having a half-life. Half the disk lived for 3 million years. After another 3 million years, so 6 total million years, I'm down to a quarter. After 9 million years, I'm down to an eighth, and so on. Okay. Now what about the observed mass function for giant planets? So by giant planet, I'm going to define it to be anywhere from 1/3 of Jupiter to 10 times Jupiter. That's because that's what the observers do. There's sort of 2 milestone works on this problem. The first was done way back in 2008. And what they found was that there's a decreasing power law mass function. If you plot the masses in terms of logarithmic bins, a 1/m distribution would be flat. This is the plot in logarithmic bins, and you see it's pretty flat with the deficit at the highest mass, which means it's a little steeper than 1/m. It's about 1.3 or so. Now you yourself forward about a decade, you get another distribution with a decade's more data. You get, again, logarithmic bins. It's flat to 0th order with the deficit at the highest value. It's a little bit steeper than 1/m. 1.3 is still a big value, or a good value. In other words, ain't nothing changed, okay? So we think we know the mass distribution for giant planets to 0th order. It's a little bit steeper than a 1/m power law. Where this fits into the grand scheme of things is that if I look at the mass function of everything, this is the stellar initial mass function. This is the 1/m giant mass function. You see that we have a deficit at the brown dwarf and then it peaks. And we think it actually goes back down. The microlensing people want it to go back up because they'll find more objects that way. There's a whole lot of uncertainty to the left of this, so we're not going to talk about it. We're talking about this part here today. So that leads to the question, how do you get a 1/m, okay? Well, this is our picture. We form a big rock. We have an extended atmosphere that eventually collapses. We have runaway accretion. But what stops it at the end? Well, again, the naive thing is you say, well, let's say the mass accretion rate has some value. We'll call it m dot. Then the mass of the planet that you form would be m dot times time, where time is the total time that you accrete. That would be the story, right? But we know the distribution of time. It's an exponential. I just showed that to you. If you're just multiplying by an m dot, the distribution of masses will be just the same functional form as the distribution of time, which is an exponential. But it's not an exponential, so this does not work. So the question is, how do you turn an exponential time distribution into a power law mass distribution? That's the mathematical issue. And it turns out to be easy. And easy's in big quotes. Okay. So we'll first write down this formula. The final mass of the planet is equal to the mass at the end of phase 2, which we know is about 20 Earths. But you can use any number you want. Then I integrate from that time to the end of the disk, m dot dt. This is exact. It's exact by definition, but it's exact, okay? But here's where the simplification comes in. I'm going to redefine my time to be t minus t2, the time left after I get to phase 2. And I'll call that t wiggle. Well, I won't call it t wiggle, I'll just call it t. But here's the thing. Because the distribution of disk lifetime is exponential, the exponential has a very specific and favorable mathematical form that at any given time, doesn't matter when you start, you're still going to lose half of your remaining bodies in the next half-life. So that means if I redefine my time to be the time since I reached the beginning of phase 3, the end of phase 2, then I integrate from 0 to t wiggle, whereas t wiggle is the time left between the end of phase 2 and the end of the disk. But the beauty of the exponential is that t wiggle will be distributed exponentially. Now that statement only works if the underlying distribution is exponential, because that's how half-lives work. But because this is a nearly exponential, it works in this case, which means that I have this formula here where I know the distribution of this ending time, and I know it's an exponential, and I know its time constant is 3 million years. So I know this distribution. I still don't know this, but I know this because of what I just did. T wiggle has that exponential distribution, right? Now, the other things I'm going to add to this is I needed some complication to make my theory work. And I'm going to have to speed up because I'm running out of time here. But I'm going to make my mass accretion rate increase with some power of the Hill radius. Will that make sense? I'm saying that bigger planets will eat mass more rapidly. You can either use 2 for the power law index, which is that you would get geometrically, or many people like to use 4 because in addition to the geometric thing, you get a shock which makes it a higher power. And then I'm going to add an efficiency factor. These are the efficiency factors I put on the previous slide. I'm just going to use 1 for today. So the picture I have is that I have material coming into the Hill sphere. And I'm going to let it do so for a time t wiggle that is distributed exponentially. Now I need to define my mass accretion rate. So the way in which I'm going to put these pieces together is the mass accretion rate will be a random variable times some set value times mass to some power given by the Hill radius to some power. So I have mass dependence in my m dot and a stochastic component to my m dot. Both of these make perfect sense. Bigger planets should eat or accrete mass more rapidly, and there should be some system-to-system, time-to-time variation in that rate. So if I do that, the mass of the planet at any given time can be integrated to give you this crazy formula. if I define T star to be this formula, note that everything here is set except for m dot 0, which is what I defined earlier. Then I can go from here to here. This is like a day's worth of math, which I'm not going to do for you. But you get a power law in mass times an exponential function in T star, which is itself a function of mass. Point being, you get a completely analytic solution, although it's an exponential function, which is almost not an analytic solution, but you can parse it. The variable that's not set is the magnitude of m dot. Instead of using that as my variable, I'm going to multiply it by my time constant from the exponential distribution, which is 3 million years, to make it a mass, and then I'm going to scale it to make my formulae more pretty. But that's just a choice. Basically, I have one parameter set, which you can think of as the magnitude of m naught, or m dot rather, or I will quote it in terms of a mass scale instead of an m dot. And then I will have a mass function for each choice of that value. And here's what you get. If you choose a small mass scale, you start to get something that's too steep that's a little bit like an exponential. But if you make the mass scale big enough, you get something that's almost like the power law. So in this case, I'm showing you the analytic description of the mass function for 3 different values of my base parameter, and the black curve is the observed. So you see I get pretty close to the black curve if I choose a large enough m dot. What this means physically is the following. In order for the planets to give you enough high mass planets before the disk goes away, I need to make the baseline value of the mass accretion rate high enough. Otherwise, the disk will all go away before the planets get big enough to populate the high mass tail of this distribution. So since I'm out of time, let me wrap up. The overview is that you can actually construct a framework for making the initial mass function for planets. You start with an exponential lifetime distribution, you let m dot increase with time, you add some random efficiency factors, and it works. As in, you can successfully turn an exponential distribution in time into a power law distribution in mass. Now, I don't have time to talk about this because we're out of time, but you can generalize this. This is just a framework that gives you the first pass at giving you a theory. You can also generalize it as a function of host mass. And there's some promise that that will work. And then I would like to bring up all the objections that you'll undoubtedly bring up in the questions, and that this is an incomplete theory. There's lots of other complications one can include. So, to conclude the talk, what I'd like to argue is that most planets form through the core accretion paradigm, from the bottom up. Some form from the top down. They're a minority. They're mostly like brown dwarfs at 100 AU. So most of the planets that we see and we call giant planets at 5 AU form through the core accretion paradigm. For that case, we can understand analytically and in some detail what the flow looks like into the Hill sphere, what the density distribution of the envelope looks like, what the velocity fields of the envelope looks like, where material falls onto the disk, what the disk structure looks like, what the luminosity contributions are, and what the radiative transfer does to give you the radiative signature of this process. We can then combine this with the material I talked about at the second half of the talk and say that this core accretion paradigm is consistent or can be made consistent with the theory of the planetary mass function that also works. And to end, let me just give you one more spectral energy distribution. This is the third one. This is the third object that we've seen that we think is a forming planet. The orange curves are those that come from the MCMC radiative transfer set of models that Aster did that I talked about, and the data are the data. But again, we're right at the cusp of being able to look at things in the sky and saying this is a forming planet. This is the spectral energy distribution. We can fit those spectral energy distributions, or just starting to, and get the parameters out. And for those of you who want to see more, there's a whole host of recent papers that go through all the detail. But I'll just leave it here and I will stop and take questions. Thank you for your patience.
So, questions? Tom?
I was just going to say, I remember your predictions for this were bimodal mostly. Some of the SED.
Oh, it depends where in parameter space. Well, it depends where in parameter space you are. When you have a sufficiently optically thin envelope, but the envelope matters, then you get kind of two humps.
Right, yeah.
But if you have a very optically thick envelope, then you just get one hump.
Right.
And when you have a super thin envelope, then you're back to just the planet and disk, and then you just get, and this one's super thin, so you basically get just the planet and disk with a little bit of envelope at the edge.
I was thinking a 2-hump might fit that better.
Oh,
excess there.
Well, the first go of the MCMC did not give us that solution, but
Is it really?
in fact, the data are kind of wonky here because there's like this and this and this, so it's probably, there's probably something going on data-wise because it's really hard to fit all three of these points in terms of the fitting to this. Because you wouldn't think that, and there's, I mean, if there was some feature there, that would make sense, but we don't know of any feature there, right? So it's,
You couldn't get a...
I suspect that they're taking with different telescopes, or that, you know, this is looking at a wider area than this one, or something. But I don't know what the answer is, but this is as good a fit as we could get, as of 2 weeks ago, yeah. So this is all pretty new, so. Maybe
You get a better fit with some of your other curves.
Oh, okay, well.
Because they look like bimodal.
Well, but then you have to, well, the other thing is that you're fitting all of this, and there's a lot of data in here.
Right.
So if you, it depends on how you weight your MC with the number of data points. The way this one's done is that all these data points here, which are being weighted as much as these guys, are driving the fit. That might not be the right way to do it. So there might be a different way to do that. And like I said, we're just at the cusp of being able to do this, right? This is the third one, right? And
It's JWST, is it? This data?
well, it's data from all over. It includes JWST, yeah. I should know more about the data. My student figured that out, so yeah. Anyway, other questions?
I'm just curious, so similar plot, you mentioned that in order to have a better constraint of the parameters, more observational data is needed. I'm just curious, for example, early in your presentation, there's an SED with a mass table or the parameters table. Like, what kind of new observations can better provide more information to constraint? It's like mid-infrared observations or just recent.
Oh, I see what you're saying. For the ones that I showed you before, if I can, I can find them. So these guys here really need long wavelength observations. So what you really like is 10 to 100 micron observations, and then what you also like is something at submillimeter, right? Because these guys, we have a lot of data on the short wavelength side and virtually nothing on the long wavelength side. And if you can get the whole thing, the characteristic of both these spectral energy distributions and those for forming stars is that they have emission over many, many decades. They're much wider than a black body. So if you really want to pin down any of them, you need data over the full range of different wavelengths, right? And these guys here are doing, we got pretty good coverage at the 1 micron, 2 micron level, and then sort of nothing longward at 10, right? So for these guys, it's long wavelength, but the other one has more long wavelength stuff and sort of a weird thing happening in the mid-infrared that I'm not sure I understand. Something looks wonky to me there, but I'm not an observer, so I don't know what to criticize, but it looks weird to me, so. There was another question in here.
So maybe a little clarification. So the circumplanetary disk only forms after the relevant equation, or does it?
Oh, well, it forms, it only, well, I have to be a little bit careful. During phase 2, you have an extended envelope. The extended envelope will be rotating, but the structure of that rotating thing will not be a disk structure because it's going to be kind of extending into that sort of weird eye-shaped hill radius. Well, it's not a sphere, but hill volume. So it's not going to be a disk. It's only after the phase 2 is over and that whole extended atmosphere collapses that you get the sort of nice separation between envelope and disk and planet that I described. So the short answer is yes, you're only going to get the disk in phase 3.
And maybe a follow-up question to this is, at least from what I know, Uranus and Neptune never gone through phase 3.
Right.
Because of their low hydrogen composition.
Yeah.
But how in this case would then the moons form around these planets are from what I know are from the circumplanetary disk.
Oh, I see. So the question is, how do you do moon formation around a failed giant planet?
Yeah.
Yeah. Well, I think that's okay. What you will have is the reason why. Well, we don't know for sure. Okay, but one way to understand what you're saying is that Neptune and Uranus and things like that are basically failed versions of what I'm talking about here. So they were going to be giant planets, but the circumstellar disk ran out of gas before they got as far as I described here. So what you'll then have is a rotating icy giant, which is Neptune or Uranus. So that part works well. But then there's going to be whatever's left over. Whatever rocky stuff will not necessarily go away when the circumstellar disk signatures that I described go away. So somehow Uranus and planets like it have to accumulate a rocky debris disk, which will make its moons. A similar thing has to happen, and I'm still fighting with people about how to actually describe this. A similar thing has to happen when you make the moons of Jupiter, right? So I think for the making of Jupiter itself with its 320 Earth masses of material, you form a disk, some version of what I said here, and the disk accretes onto the Jupiter and stuff. Then at the very end of that phase, you have to make the 4 Galilean satellites. But the 4 Galilean satellites are not made out of gas, they're made out of icy, rocky stuff. And the easiest way to do that, which is not at all obvious from anything I've said, is to actually have material come very close to the Jupiter and migrate outward instead of inward, which is kind of an inside-out disk. Now that can't happen during the actual formation of Jupiter itself, because if most of the material were going out, you would never make Jupiter, you needed to go in. But to make the moons, it's better for it to go out. So what I suspect happens is that there's the gaseous accretion phase, that's what I'm talking about here, and then there's a later phase where the rocks do the rock thing, and they may well move outward during the moon formation epoch. But how the rocks get there and when they get there and the timing of it there's not a great theory for that. But you're kind of much less constrained, because all the disk signatures that I said when I said the disk lifetimes are 3 million years, basically all the disk signatures we know about, veiling, accretion onto the star, the actual infrared excess, those are all gas signatures. Once the gas goes away, you can still have rocky bodies and debris disks around the stars for much longer than the 3 million years I talked about, which means you still have those rocks in play in the circumstellar disk to make your moons of Neptune like you want. So you have the raw material, that's not a problem. The problem is I don't have a good theory that describes it for you. But maybe that's something you can do. You're young, you can solve it.
And maybe another question. Do you think the fuzzy internal structure of Jupiter and Saturn has to do with that?
Can you be a little louder, sir?
Do you think the fuzzy internal structure of the gas giants has to do with that formation process?
Well, I'm not 100% sure I understand the question. I mean, certainly the starting point of the internal structure will be influenced by the formation process. In the Jupiter formation, world, they talk about the difference between a hot start and a cold start. And what they mean by that is when Jupiter first becomes Jupiter and has ended its accretion, is it sort of a high entropy state of thermodynamics or a low entropy state, which essentially means in terms of practical, is it big or not so big? Or how big is it, right? And you can codify that by making a stellar structure or planetary structure like calculation and saying what's the entropy per baryon of that. And whether it's high or low determines on whether you're in a hot state or a cold state. And whether you're start hot or start cold depends on the way in which you build up the planet. So that very much, so long story short, and I'm rambling here, long story short is that the initial size of your Jupiter when you call it at the beginning depends on the formation history. Now, if you then wait millions and 100 million years, all of those evolutionary things will converge to the same evolutionary track and wash away that initial condition. So once you look at the billion-year-old version of Jupiter, it won't matter whether you started with a hot start or a cold start. But if you look at the 10 million-year-old version of Jupiter, it will. So the starting state depends on the formation epoch. Now, the other thing that we know, or we think we know, there's an argument that's, again, beyond the scope of this talk, but you can actually make an argument for what Jupiter itself had to have, how big it had to be when it was born. The answer you get is a nice number, it's 2. It's twice the current radius. And if you ask on the hot start versus cold start continuum, it's sort of it's intermediate. It's kind of a little bit warmish start. And there's a couple different independent lines of evidence that give you that as the starting, that value as the starting state of Jupiter. So there's a little bit of evidence, just a little that's coming, that things start sort of in between hot and cold starts. But this is all preliminary, so we'll know a lot more in 5 years, so. Or 10. Other
Okay.
questions?
So, okay, if there's no more obvious questions, let's conclude the colloquium. Okay, thank you. Thank you.